Good, good evening. Can you hear me? Okay, thank you for your response. So we will discuss seventh assignment here, and it's 18 question total. So let's discuss first question. Question is calculate the movability of the electron having an electron mean free time of 0.1 picosecond at 300 Kelvin. Also calculate the mean free path assuming mass of n equal to 0.26 mass of test mass of electron. These calculation. So these are the option. How can you calculate? So please try to solve this question. Here is tau is given picosecond equal to 12 second. Temperature also given. Mass of electron equal to 0.26 mass of test mass of electron. So how can you calculate the movability? Also the mean free path length. Let's say L. Please try. These are the given information. Based on given information, please try to solve this question. I am giving to you 5 minutes. You can take 5 minutes to solve this question. Then I will discuss. So first, please calculate the movability. Did you get your answer? You can use this formula for movability calculation. So let me put the value. Q is the electronic charge, anti-coulomb, and minus 12 second tau and 0.26 m naught. And please use clear up to this point. Okay, thank you. So please solve this calculation. Tell me the answer. And how can you calculate the mean free path? You know, kinetic energy equal to 3 by kt. Another formula. So here you please find here VTS, then use to calculate mean free path, and now solve this equation. So first tell me the movability. This is the unit, centimeter volt per second. Did you get this answer? This is around, I think, and unit is meter volt per second per volt per second. then convert to centimeter. You will get. Did you get this answer? Okay, thanks for your response. 1 minute. Now for we have the relation if and then velocity of electron. You can use the thermionic energy. You can use to equal to half of is cancelled 3 kT. So put the value in this equation and what is mass of electron? 0.26 times something. It is 0.26. Not. KT value at 300 Kelvin is 26 volt. So now please solve this root square. Tell me the answer. It will be around 2.2 in centimeter per second. Try to solve this. After this, velocity and relation between time. So use this. Tau is given. Second. So put these values here. In tau. So it will be 10 to 12, 7.1 multiply 2.2 minus 6 meter. Not in meter. Centimeter is already there. So this is the answer. Any confusion or any doubt? Okay, thank you. So this is the procedure. Please use to this procedure to solve like this question. Next question. Which of the following type of silicon exhibit the lowest carrier movability? Which type? And lower carrier movability. This is why lower carrier mobility exhibit amorphous. Why? Is there any reason? We have already solved movability question. So, 1 minute. Impurity and lattice scattering dependent factor. So, impurity, yeah, good. Higher defect density. So, you can read also in solid state, the electron mobility characterize how quickly the electron can move through the metal or semiconductor. This is the definition. When pulled by electric field, there is an analogous quantity for holes, same called hole mobility. The term carrier mobility refers general to both electron and hole. Electron and hole mobility are a special case when the electric mobility charged particle in a fluid under applied electric field. When the electric field E is applied across the pi faces of material, the electrons response to moving the average velocity called drift velocity Vd. Then the electron mobility is defined as Vd equal to mu E. Okay, for semiconductor mobility depend on the impurity concentration, including donor acceptor concentration, defect density, concentration, temperature, electron and hole concentration. It is also depend on the electric field, particularly at higher field when the velocity saturation occur. It can be determined by the Hall effect. So we can also calculate the mobility from Hall effect or infrared from the transistor level. So next question. The starting material in manufacturing semiconductor grade silicon is okay. So D is your correct answer, and you can see the procedure. Trichlorosilane is used and give the temperature 1100 degrees Celsius. Then SiCl4 goes to silicon. Okay, so this is the process. Here you can see the reactions. Trichlorosilane. Okay, so trichlorosilane, the cement process which is used, the most commonly method for manufacturing semiconductor grade silicon. Start with trichlorosilane. Trichlorosilane is obtained from metallurgic grade silicon through a reaction hydrochloric acid. You can see the process involves chemical vapor deposition CVD where When trichlorosilane is decomposed on the heated silicon rod to produce high purity polycrystalline silicon. Yeah. Okay. So next, this is the next question. I'm coming back. Give me 1 minute. Hello. Second generation solar cell technology. Yes, please answer. So BME is the answer, and you can see from the lecture, second generation solar cell, thin film solar cells, primarily on the northern metal to reduce metal cost and reducing the amount. So amount of silicon, sorry. Okay, so answer is B and E. These are the amorphous silicon and cadmium chloride. These are the second generation solar cell, and which is based on thin film solar cell. Okay, next, the process used to manufacture semiconductor grade silicon is a union carbide also and cement process. So cement process is we have already seen to use semiconductor grade silicon, and also you can see cement, union carbide, and ethyl incorporated process, but yield is only 15%. So cement process is used for higher yield. Okay, Next question. Yeah, this is the good question. Let's solve. Plot the doping concentration as in a distance 30, 40, 50, 60 centimeter from the seed in a silicon ingot 100 centimeter long that has been pulled from the melt with the initially doping concentration 10 to the power 17 per centimeter cube. Get on for also is 0.3. So how can you solve this question? So this is the given parameter cannot initial concentration cannot sorry per centimeter cube cannot 0.30 each cannot is 100 centimeter and it's 30 40 50 60 and 70 centimeter. Plot doping concentration as unit distance versus 202 plot length versus CS concentration. So you can use this formula. Okay, so please use this formula. Try to solve out CS. Let's say L430. I am calculating centimeter. L is L0 is center. Okay, so please solve this. You will get around. Similarly, please solve for 40, 50, 60 and 70 in same way. You can take for this 5 minutes. Please tell me the answer for 40, 50 and 60 also and 70. This is for method. Please try to solve. Sorry, my network was lost. So, let me share again my screen. Oh, sorry, we are here. So, got it? Yeah, I think it's clear to up to this stage. Okay, thank you. Similarly, please tell me the answer for next. Similarly, we can calculate for 40, L40, CS equal to C naught cannot L by L naught 40 by 8 minus 0.7. Similarly, for L50, let me write also power. So 10 to the 9 to 10 power takes that. 450, this will be the same. Please calculate L460, and L470. Sorry. So calculate this English calculator. 135, 8.2460 per centimeter cube. Similarly, 1 to the power. Right? Please check your calculation also. And for 50. And we have already calculated for length of the yes. So this is around 4, 5.5, 6, 7, 8, 9. This is where like that. Let's say this is 430 centimeter, 40, 50, 60, and 70. This is around 3.85, 5.5, 6.2, 7.3, 8.9, and 10 to the power last 10. This okay, so plot will look like that. Not in a straight line, but like okay, clear. Any doubt? So let's move for next question. Which of the following are the correct sequence for manufacturing the single crystal silicon? These are the four options. Please choose your answer. Then I will discuss. So answer will be C. And first, metallurgical grade silicon and MG silicon production obtained from quartz SiO2 reduction using carbon. Then purification. Then converts after purification energy silicon into semiconductor grade silicon via chemical purification, cement process or fluidized bed reaction, and melting and solidification. Semiconductor grade silicon is melted and solidified using process like Cholesky and Frodzon method to grow single crystal. And single crystal silicon formation, the pure defect-free crystal is formed. So single crystal is highly pure, defect-free. So first is metallurgical grade, then purification, then semiconductor grade silicon, then melting and solidification, then we get single crystal, defect free. Okay, next. Yeah, this is the question. Cholesky melt is simultaneously doped with boron to a level 10 to the power 17 atom per centimeter cube and phosphorus to level 18 to the power 16 atom per centimeter. Thus, PM junction is formed during the growth. If so, then what is the fraction solidified? These are the given parameters. Okay, so how can you solve this question? Thus, PM junction is formed. So let's say yes. So concentration of P boron and P type and will be same at the junction. Okay, this is the condition. So you have to calculate. Let's say yes. Cannot say no. You can use solidification in the M naught. And by you have to calculate. This is solidified fraction. So how can use this formula? Let's suppose says for boron and phosphorus. C naught for boron and phosphorus. What is this value? For boron 20 power 17 per centimeter cube initially. K for 28 for CS. Then for what is phosphorus 18 per centimeter cube and K naught for P. These are the given value. Please use this value in this equation and apply this condition. Try to solve. Find the M by M naught. You can take 5 minutes for this question. Let's try to solve. So put this value in this condition. Did you get answer? Let me put CS4 possible plus V naught equal to, okay, so this is the situation. Now we have to solve this equation. For this equation, 17, 16, this is goes out. Next, we come to okay. This is the remaining term. And then let's try to solve this. After the minuscule control, you will end up with okay. Cancel out some. This represent now one check the square root of 4.45. Then calculate this. This will be okay. And finally, clear or any doubt? Okay, thanks for your response. Next question, let's discuss. Which of the following belong to the family of chalcozamides? So these are the answer: cadmium sulfide and cadmium telluride. And let's see what this is. Chalcozamide is a chemical compound consists of at least one chalcozamide anion, at least one more electronegative element. Although all group 16 elements of the periodic table are defined as chalcozamide. In terms of chalcozamide is more commonly reserved for sulfide, selenite, telluride, and polonite rather than oxides. So many metals are or exist as a chalcozamide. Next question: which of the following are commonly impurity element in metallurgical grade silicon are used? Please tell the answer. Okay, and not only aluminum, calcium also openly found in metallurgical are judicial impurity from the raw material used to production. Aluminum is commonly used. Okay, aluminum and calcium. So you can see from the lecture production of metallurgical grade silicon impurity have liquid silicon Fe.2 children that much TiCa carbon. Okay, so this is generally used. Next question. The intermixing of cadmium sulfide and cadmium telluride layer are in cadmium telluride leads to increase the quantum efficiency or decrease the quantum efficiency at respectively higher or lower wavelength. So this is the question. Please choose your options. Right options. Got to it in which option is correct. So let me tell you the answer. Decrease in quantum efficiency at lower wavelengths. So intermixing cadmium telluride and cadmium sulfide during cadmium telluride cell leads to formation of cadmium sulfide X minus tellurium 1 minus X alloy. This alloy is formed and at the interface. This alloy has higher band gap than cadmium telluride and can impact the quantum efficiency of the solar cell, particularly at shorter wavelength. And cadmium sulfide has bandgap 2.42 eV electron volt, while the cadmium fluoride has 1.45 eV. When intermixing occurs, it creates a region with higher bandgap than cadmium telluride. Obviously, two bandgap higher and lower are mixing, then intermixing material will be the higher bandgap from lower material, which is absorb fewer low wavelength, higher energy photons. This result is decrease in quantum efficiency at lower blue region spectrum. This this is this is blue region response and this is red response due to rare surface recombination. Beyond the bandgap, matter doesn't absorb any light. So this is bandgap dependent questions. Okay. Next, P-type character of the gallium arsenide can be announced by P-type. Please choose your answer. So answer substitution arsenic with zinc. N-type doping, you can use this SN, SISC for P-type. Zn, Mg, carbon or A site. Okay, absorption coefficient versus you can see the band gap. Okay, to enhance p-type character of galliums, we need to introduce acceptor dopant to create hole in the material. This typically happens when the group second element like Zn, B, or Mg replace group third element. Okay, answer is correct. This create acceptor level and increase the whole concentration. So, signing with Jim. Next question: which of the following can be used to window layer in gallium arsenide solar cell? Yes, please choose your answer. Okay, see. Sorry, answer is B and D. In a solar cell, window layer is a material that allows light pass through while minimizing carrier recombination and absorbing photons itself. The correct choice should be have wide band gap and good lattice matching with gallium arsenide to reduce absorption and enhance transparency, to prevent defect, to improve efficiency. Wide band gap and good lattice matching. So Indian aluminum air will use for window. So, so you can see Indian gallium arsenide, aluminum gallium arsenide are used. Next question: cadmium chloride treatment in cadmium chloride solar cell results. Which option is correct? You can see the explanation also. Choose your right option. Yes, please. D. Yeah, your answer is correct. 1 minute. It is slow. So, so cadmium chloride are used to large grain size in cadmium chloride film and reduce defect density. So larger grain size and reduce defect density. So cadmium chloride treatment helps to recrystallization, lead to grain growth, which reduce the grain boundaries, improve the charge transfer, and reduce defect density in cadmium chloride. The treatment passivate defects in cadmium chloride film, reduce recognition center, and improve the carrier lifetime. Okay, next question. N-type character of cadmium chloride solar cell can be improved. These are the options. Please choose your right option. Okay, B and C. Your answer is correct. Let's discuss. Doping with indium. Indium is a donor impurity in cadmium chloride, meaning it donates free electron, enhancing the N-type characteristic. Cadmium interstitial extra cadmium atom occupy interstitial site can act as a donor, also increase N-type conductivity. Cadmium vacancy, these correct acceptor and enhance p-type. So this is used for p-type. Doping with gold. Gold typically acts as an acceptor. Impurity improve the p-type conductor, not n-type. Okay, so B and C is the right answer. Okay, next question. Cadmium chloride treatment in cadmium chloride solar cell results in. These are the four options. Please choose your answer. Then I will discuss. Yes, please answer. Your answer, please. So let's discuss option A and B is so use as copper as a back contact. Copper helps to form a ohmic low resistance ohmic contact with cadmium chloride to improve hole collection and enhance performance. And heat treatment in oxygen. Oxygen treatment helps to passivate defects and improve grain boundary properties, leading to better carrier transport and efficiency. Views on fine grain boundary. Larger grain are generally better because of their reduced grain boundary defects and recombination losses. In cadmium telluride, intermixing between cadmiums and too much intermixing can degrade the junction quality and leading to reduce. So this is losses, recombination losses and reduced efficiency. So these are the heat treatment and these are the correct way. Okay, so this is last question for today's session. I think. So we have discussed. Let me show you. First question on movability of electrons. So please use this formula. Remember what is phosphorus oxochloride treatment in solar cell? Which question in this slide? Okay, okay, not in PPT. I will tell you later. Please let me show these we today discuss question. Then I will discuss to your doubt. So first question we have discussed on movability and mean-free path, and also we have a picture dependency to 3 to the power movability with temperature minus lattice scattering and impurity to the power 3 by 2 and minus 3 by 2 lattice 4 lattice. And so this question silicon exit lower carrier mobility. Okay, we have already seen due to the higher defects and silicon semiconductor grade silicon trichlorosilane are used initially, and second generation solar cell thin film. So next, the process used to manufacture semiconductor grade silicon is a union carbide process in cement. But 60% yield from cement process. Okay. Next, we have discussed the plots based on the concentration variation from the lens initially in anode silicon, and discuss this question plot solve. Next question we have discussed process step by step manufactured on single crystal. So this is the process. First is metallurgical grade silicon, then production purification, then SC semiconductor silicon grade silicon, then solidification In last, pure, defect free, highly pure, single crystal is highly pure, silicon is obtained from. Okay, next we have solved this question. Cholesky is simultaneously doped P and N, then obviously PN junction is formed, and then we have applied the condition, then solve this question. Next, chalcogenide families. So this is the explanation. Please see. In between my internet is slow, so that's why I'm repeating the question. Okay. Next, which of the following are commonly impurity element metallurgical grade silicon? So not only aluminum, calcium is also used. Next, yeah, intermixing cadmium chloride solar cell leads to. So we have discussed, and this is the explanation. Please see. Next, p-type characteristic gallium arsenide can be enhanced by. So n-type and p-type, you can see these are the dopant will use. Next, which of the following can be used to ventilate gallium arsenide solar cell? So indium and aluminum. Okay, and cadmium chloride treatment for laser grain and reduce the density. Next, n-type characteristic dopant with aluminum and cadmium interstitial. And this is the last question, and I will come to your doubt. What is the phosphorus oxochloride treatment in solar cell? Yeah, name is clear. Treatment. Okay, so treatment is generally used to reduce the sorry, defects. Okay, so reduce we know only generally is top surface or so for this POCl3, so phosphorus oxide is this is chemical dopant. In between the material also not only the surface defects, also in the bulk has a defects. So to reduce the defects, we will use the treatment POCl chemical to create n-type layer on a silicon wafer. So We have used chemical dopant to POCl3 to form n-type silicon wafer, which is we know essential for post PN junction to form PN junction within the solar cell, and which is increase the efficiency, charge carrier, and movability. So this treatment is used to improve the efficiency of solar cell via reduce the defects in silicon wafer to form n-type character. So n-type is movability of electronic is higher than the whole to improve the these parameters. Okay, so this to leads to higher efficiency. Any doubt? The okay. Thanks for your interaction in whole session. So this is all about for today's session. We will meet in next Monday. Then we will discuss past eight assignment. Okay. If you have any doubt, you can ask in upcoming session also. Okay. So let's thanks and close the session. You don't have doubt. Okay, we will meet in upcoming Monday. Thanks to all of you. Like, thanks.